I'm Sean, part of Group 21. Our project is getting a robot to catch a pendulum. Not if you can show our setup right now. So as you can see, we have Baxter with the Connect on top. And this is our pendulum right here. Everything is actually a free model. All the parameters are free, except for the one thing that we've measured is the length of the string itself. That's the only constant that we're talking about. So, let's see it in action. So the first step that we'll do is we'll look at the launch file. The launch file essentially starts up the robot, starts up the camera, gets everything working, RVs, the ball, etc., etc. Alright, okay, so the first step, in order to do the tennis ball tracking, we need to define an area, that way it doesn't give into noise. So if we look, so I'll define an area right here. So 1, 2, 3, 4. Okay, and then we can confirm the selection, that way if we choose a bad one, we could always restart it. So yes, I like that one. And if we look, you can see it's tracking the ball perfectly there, and it's also projected on the Baxter string up there for easy debugging. Alright, after that, we compute, in addition to the launch file, it's also computing the transform, and it's also placing the ball in the world frame itself. That way we don't have to worry about the full transformation. So if we look at RViz, we can see that the ball appears in the model itself, which is a pretty accurate location. If we want to do this even more, we can put on the point cloud, and if you look, the ball's exactly where it should be. So, yeah. Alright, so after this, the next job is to plug it into the model. Okay, so the model basically, we've done all the math, we did the dynamics, it basically constructs the entire pendulum in 3D space, converts the frame and things accordingly, that way you can predict where it's going to go. So the first step is to calibrate the model. So we start with one step, so I'll press enter, calibrate it, put it at the center. Basically, you can look right here on the screen, you'll see we get the pivot. So it tells us where the pivot location is, and then from there we can construct the model. And then after that, Cam here, to put it where I want it to be, Cam can do a couple practice runs to see where it wants to be. All good. That's you. All good? Okay. So if you look, so when I press enter, I'll take 50 samples of where the ball is to account for extra noise because the ball is so small. And then I'll plug it into the model to solve the inverse problem. And from here, here's a 3D graph of the pendulum model that we get, where this is the start point, this is the calibration point, and this is the end point. The way that we decide where to go is we define a sort of plane right here, and we say what's the closest point to go, and we decide the coordinates that it will reach. And from there, it's done computing the trajectory, and knows where it wants to go. Then the next step, the last one, is to actually compute the path itself. So this is just plugging the trajectory into moving. In addition, we have some extraneous math and models that we did to get the appropriate orientation. That way, it catches it in the correct way. So let's compute the plan. So you can see it goes to the correct location and the correct orientation, ready for catching. And if we look, we're going to calibrate the gripper real quick. Alright, and if we look, here we go, it's open, and if we throw the ball, we catch the ball. And that's the whole model. Thank you very much.